Okay, so let's go ahead and get started. I was trying to figure out what is the best way to set up my recorder on this particular computer, and still working on that. But I don't want to take up class time. At the end of the class, can somebody try to remind me to upload the video before I get out of this room? Because I forgot last time, and by the time I walk out, I go like, "Dope! I forgot to upload." And because everything is on the RAM disk, the moment I reboot the computer, it's all gone. So I'm still trying to figure out what is the best way to do this, but at this point, I don't have a very good, reliable way to do it yet. Okay. So there we go. All right. So how was your weekend? What weekend? All right. Okay, so let's get back to predicate logic or predicate calculus. And because the recording last time did not quite work because I couldn't upload it, or I forgot to upload it before I turn off the computer. So what we'll do today is we're going to revisit predicate logic. But this time we'll start with the example, the Jedi example, just so that we have something to work on, and then we can go back and explain some of the concepts. Okay. And the part that I'm referring to is right here. Let me just zoom in so that we can see all the text. All right. So skipping a whole lot of stuff. Okay. So we start with these two particular predicates. And say, okay, what do these mean in Prolog? Prolog is a programming language, and it is very closely related to predicate logic. In other words, it is an implementation of predicate logic so that we can use a computer to do all the processing. Okay. So in this case, we have two what we call clauses. Okay, and each one is a rule already, but it's a very simple rule. These are what we call facts. When you use predicate logic, or when you use Prolog to be more specific, if something starts with lowercase, it is usually either the name of a predicate or the name of an atom of the universe. So in this case, OB1 is quote-unquote an atom of the universe, or in our terms, it is an element of the universe of this course. It's one of the things that we're interested in this particular program. So OB1 is actually in the domain D, and we are basically saying is a Jedi is true, because what this really is equivalent to is a Jedi is true. Okay, let me show you what the general rule looks like. Okay, this is something that we have seen before. So when we look at this particular clause in Prolog, it's basically reading backwards. You have to read backwards. It means is a Jedi X implies can use lightsaber X. Okay, so you read it backwards. So in this case, in the first case, when you do not have anything on the second part, it means true implies is a Jedi Obi-Wan. Is that okay? And if true implies that means it has to be true, because in an implication, if the first part is true, the second part has to be true. Is that okay? All right, let me just use a text editor here, just so that we can see, instead of just talking about it, we can actually see what I mean when I talk about that. Okay, so is a Jedi Obi-Wan with a dot here is really the same thing as it's a shorthand of saying is a Jedi Obi-Wan only if it is true. These two are exactly the same. And let me see if I can bump up the font size. Last time we tried, and I was not able to change the font size. So maybe I didn't. Yep, it wouldn't update the font size either this time, which is kind of odd. Let me try the usual shortcut keys. Nope, that didn't work. Okay, I don't really see any other way to change the font size.
Highlight it? You have to highlight what you want.
I don't think so. This is just a text editor. It's really the same thing as a notepad. So if I change the font size, that really should change the... Okay, let me pick another font. Maybe it's a font issue. So we'll pick another font. Nope, that did not change either.
Can you just zoom in?
I tried that too. It didn't work. Well, if you want to... Okay, we can do it this way. Okay, don't cancel yet. Control C. Okay, we'll use an excessively complex tool for something simple, but it will still work. Or I can go for Google Drive, use a Google document. That may actually not be a bad idea. Have one single folder on my Google Drive to share with the class, and then everything I do, I use a Google document. Let's try that too. Sorry, I keep changing my mind. Los Rios. So I went to the second last field target match yesterday. Basically, a bunch of guys, shooting air guns while they're chit-chatting the whole time. It is equivalent to the men's version of a quilting club. Bunch of guys sitting down, they pretend to be actually shooting targets, but they're actually chit-chatting all the time, the entire time. And most of them are retirees too. Okay, so I'm going to set up a folder that is shared and specify how it's going to be shared. And let me go to advanced. We'll just go ahead and make it everybody can read it, whether you are in my class or not. Okay, so anyone with the link can access. No sign in is necessary. And those who can sign in can view. Okay, that's good. Save it. And copy the link. Go back to Moodle. Actually, I can do this. Open a new tab. Go to News Forum. Post it here. Okay. Shared class folder in Google Drive. It's right here. Accessibility, people would frown on this. Oops, nope, not that. Oh, stay on page. Nothing to upload. Okay, maybe we just back up. Okay, one more time. Of course, I can do this and do the link like that. There we go. Okay, and mailed it right away. So if you want to check your Google right now, because I know some of you have devices, you can check it right now, and you would be able to actually see the document that I'm creating in class as I'm working on it. Okay, so we're going to create a Google document. Yes. There we go. And the first thing we change is the name of the file. So we'll just name it after today's date. And today's 2/4. There we go. Now we can change the font size all we want. So we can say zoom. I think the usual zoom control works. There we go. And we want to change the view from print layout back to the usual web presentation. I don't need a ruler for this. And don't try to check my spelling. There we go. So let's go ahead and paste the content. Oh, I forgot I changed the... Okay, do it one more time. Switch back, paste. Is that better? 5 minutes later, right? It's better. Okay. So,
Make the font bigger.
make the font bigger.
Thank you.
We can certainly zoom. How about that?
Yes, sir.
Yeah. Modern technology. Okay, so in this case, the first one is a Jedi in parentheses Obi-Wan is a shorthand of the second one, which is a Jedi in parentheses Obi-Wan only if true. Okay, or the normal way to read that is true implies is a Jedi Obi-Wan. Okay. In other words, this one, okay, let's see if I can, is the same thing as insert equation. And the best part about Google equation is it actually understands LaTeX shorthands. So this is really saying one right arrow is a Jedi Obi-Wan. So when you have true implies something, that something is automatically true, which is basically a long way of saying it's a Jedi. Obi-Wan is a Jedi. This is an assertion that Obi-Wan is in fact a Jedi. Is that okay? So this belongs in iota because the set of iota gives you all the known to be true facts. So this is basically, yes, it is given to you that Obi-Wan is a Jedi. Is that part okay? Okay. So moving on to this part here. Okay, I'm trying to keep track of. There we go. So we also have a second clause that says Luke Skywalker is a Jedi. Okay, apparently this is after a certain point in time. Okay, and so Luke Skywalker is known to be a Jedi as well. Yep.
You have the is a Jedi Obi-Wan and then the is a Jedi in the prologue symboled in true. You said those are the same thing?
Yes.
Okay, one's just in prologue?
One is just a shorthand. So this one,
okay.
So when we switch back into, okay, I better close the other one so it doesn't interfere. Oh, it's another tab here. So there we go. So it's really just a shorthand. This is really a shorthand of this one.
Oh, okay.
But because only if true is really kind of redundant, so most of the time we just use the first format and not the second format. Okay. Any other questions? No other questions? So let's move on with the discussion here. Okay, so this is really great because at this point we are at the same place that we were in propositional logic, which means we can specify facts of specific things. But what about quantifications? Because that's one of the biggest strengths of predicate calculus as opposed to propositional calculus. Okay, in propositional calculus, we cannot say for all or there exists and make an association based on quantifiers. But in predicate calculus, we can. So in this case, we can use a rule like this. Okay. Now remember, you have to read the rule backwards. So this is basically saying, if X is a Jedi, then X can use a lightsaber. Okay. In other words, when you look at let me just copy and paste this one. So when you look at this particular clause in prologue, it really is stating the following. Okay, so it's really stating the following as a logical statement. Okay. Now, first of all, if you have a variable that is appearing in the head portion, this is called the head portion of a prologue clause or sentence. Actually, this is called a sentence. So this is the head part. If a variable, in this case, uppercase X, is on this part, it is called a bound variable. Okay, and not only is it bound, it is also using the what we call the universal quantifier to bind it. In other words, we're basically saying for all X, this blah 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 blah. Okay. So let me go ahead and type in the equation so that we can actually see the equivalent logic statement expressed in prologue in this case. So we basically say for all, okay, X. So this lowercase x is equivalent to the uppercase X in the prologue code, except in this case I use lowercase x because it's conventional in a mathematical equation that we use lowercase letters to mean variables. Okay? If you want to be redundant, you can always say x in D as in the domain, because D is our domain. It is also called the universe. It is also called the universe of this course. Those three names, they all refer to the same thing, which are basically things that we are interested in this particular universe, in this particular prologue program. Okay, so most of the time people don't even bother with that, but if you want to be extra clear, we can say that because it is usually just implied, so it's not a big deal. Okay, so what do we want to say about this x here? But remember, this applies to all x's. Okay, everything in this universe, whatever I want to state in the parentheses, is going to be true. Okay, well, in this entire universe, we have all kinds of stuff, right? So we have people, we have Jedis, we have Siths, we have stormtroopers, we have tools like lightsabers, blasters, and rocket launchers. We have equipments like X-wing, okay, TIE fighters, individual TIE fighters. We have robots. We have R2D2, CP3O, and so on. So what can we do about that so that we can say that X is a Jedi? If X is a Jedi, then X can use a lightsaber. We use an implication. Okay, we use an implication. And I'm not sure whether it will take this. Let me see if it will do this. Is a Jedi close? Nope, it won't do that. So I'll just use is a Jedi. Is a Jedi. This is a predicate. It applies to the variable x in this case. Okay. So a predicate is basically something that can either be true or false depending on the parameter. So in this case, this part is not an assertion. It is really just asking a question. Is X a Jedi? Because in this entire universe, certain things are Jedis and other things are not Jedis. But this is saying, okay, when we finish this sentence, then it will make more sense. It is basically saying if X is a Jedi, then X can use a lightsaber. Because this is another predicate which can be true or false. So what this is really saying is, if X is a Jedi, if you can make the first part of the implication true, the second part has to be true, which is X can use a lightsaber. Is that part okay? Are there any questions about, the statement in prologue as opposed to the mathematical representation of that same statement? Yep.
Why are you using D as a set?
D is our domain. It is somewhat redundant because every time we refer to some variable, it has to be an element of the universe of discourse or the domain.
Okay.
But D is really our domain.
When you said X or D was what we were interested in.
Right.
X's or D?
X.
Okay.
Yeah. So the part about X is in the set D is usually considered redundant because everything that we talk about has to do with things that we are interested in that universe. So that part is usually left out, but we don't. In this class, we can be a little bit more clear, at least at the beginning. Is that part okay? Okay. So later on, we'll find out. Okay, so given these two sentences, okay, given this part here, which is basically saying Obi-Wan is a Jedi, is an assertion that Obi-Wan is a Jedi. And given this particular statement here, now this statement is true to begin with, but the question is, how do I know that Obi-Wan can use a lightsaber? How do we hook up these two? Now, in your mind, I'm pretty sure it makes sense already, okay? Because in English, okay, in your daily application of logic, if I tell you that every Jedi can use a lightsaber and Obi-Wan is a Jedi, you make that connection right away and say that, oh, okay, Obi-Wan can use a lightsaber, okay? But we want everything to be mechanical in this class because we are dealing with computer science. So we want everything to be mechanical so that the computer can actually do the same type of reasoning as we can. So we'll talk about that later. So right now we're just talking about the syntax of, okay, this is how you do things in Prolog, but this is actually what it means in terms of logic. This is what you specify in Prolog, and this is what it means when we are dealing with just the logic. And if for those of you who really want to use an English version of this, we can also do that. Let me turn off all the formatting, clear formatting. So we can say in English, this is really saying the same thing as if X is a Jedi, then X can use a lightsaber. Okay, so 3 forms. Okay, one is Prolog, the second one is in mathematical symbols, and then the third one is just stated in English. Yep.
Did you use a different capitalization on the X's for you?
Oh, okay, nope. It's just me being inconsistent. There we go. All right. So then we can move on and talk about other, other stuff that you want to express. Okay. So we keep going like this, and then I explain what the symbol means. This symbol here, which is in the document right here. This is basically saying only if. Okay, which is another way of saying, oh, the second part, the part to the right hand side, is the first part of the implication, and then the other part on the left hand side is really the second part of the implication. Okay, so that's basically just saying only if. Okay. All right, so we can do a lot of fun stuff. Okay, we can state ownership of items, because green hack in this case is an element of the universe. It's not a person; it's a tool. And Luke Skywalker is another element of the universe. How do we know that Luke owns, green hack, the lightsaber? Well, this states just the ownership part. Okay, which object owns which other object, and then this part basically say what it is. Okay, green hack is a lightsaber. So these are all individual facts. In other words, they should be all elements in iota, because these are basically facts that are given to you, known to be true. Are there any questions about this? Okay, no questions? All right. So now we can specify more important rules. Okay, so the predicate that we want to express is this one. Okay, so let's take a look at this mathematical version first, and then we'll talk about how to represent it in Prolog. So what we want to express is a Jedi implies, if X is a Jedi, it implies that X owns, that Jedi owns a lightsaber. But that may or may not be the case. So what we want to do is to use, it's a proper Jedi. So certain Jedis may not own a lightsaber, at least for a short amount of time. So the way we look at this is we look at this and go like, okay, if X is a Jedi and X owns a lightsaber, then X is a proper Jedi. Okay, that's basically what it's saying. But in this case, we have a free variable. Okay, what a free variable is in this case is Y. A free variable is one that is in the body instead of the head of a prologue sentence. If a variable is only in the body but not in the head, it becomes what we call a free variable. X is not free because X is actually in the head as well. So X is already bound by a universal quantifier. A free variable in the body is not bound, okay, by the for all or the universal quantifier. It has its own existential quantifier as a part of the body. Yep, go ahead.
I was just going to ask if that's what translates into the mathematical version up there where you've got...
No, it's not exactly the same.
For all X.
No, it's not. It's not exactly the same because it's a proper Jedi in the predicate in the mathematical version. So what I state here, this is expressed as follows in Prolog, is actually wrong because I forgot to update the other one. Is that okay? I forgot to update this one to reflect that it's a proper Jedi. A proper Jedi is one that owns a lightsaber.
So the concept of Y being a free variable doesn't necessarily translate into the other syntax?
It does not translate into this one. So we'll go ahead and take a look at what this actually translates to in mathematical symbols. So let me copy this into here, and then we'll take a look at this one. Okay. All right. So first thing I do is to take out the formatting. So go to Format and Clear Formatting, because otherwise it will look green. Okay. So we look at this one and go like, okay, but what does it look like in actual mathematical symbols? So we'll go ahead and insert an equation. Okay. So remember, we have to kind of read it backwards. So instead of working on the quantifiers first, this time I'll just work on the predicates first. Okay. So the predicate is basically just saying is a Jedi X and owns X owns Y and is a lightsaber, okay, Y, okay, implies is a proper Jedi 1, because we have it's a proper Jedi 2 later on, X. So when you look at the actual just implication itself, this is what it's stating. Remember, we read it backwards. The body is really the first part of the implication, and then the head is the second part of the implication. So the way we read this is X is a Jedi, and X owns Y, and Y is a lightsaber, implies that X is a proper Jedi. But this is all without quantifiers, okay? So now we need to throw the quantifiers into this whole thing and go like, okay, so which one is for all and which one is there exist? Everything in the head, all the variables involved in the head are for all, okay? So they're all bound by what we call universal quantifiers. In this case, it is X. So we say for all X, that's outside of the equation, that's why it didn't work. There we go. For all X, okay? So I'm not going to use in D because everything is in D, okay? So I'm not going to specify that anymore. So X is already bound by the universal quantifier, but Y is not, because Y is not a part of the head, and all the variables that are in the body but not in the head are what we call free variables.
Sorry if I missed this. What do you mean by in the head?
In the head means this part. This is the head of a prologue sentence, and this is called the body of a prologue sentence. Okay. But because X is a variable involved in the head of a prologue sentence, it has a implied quantifier applied to it to basically bind it. Okay. So for all is applied to X. What about Y then? Well, because Y is a free variable, it is in the body, but it's not in the head. So the only quantifier that applies to Y is there exists. So inside here, okay, we say exists Y, and then I just have to add one more level of parentheses just to match the parentheses. So in this case, the for all applies to X, the there exists applies to Y. In other words, do you think a Jedi needs to own every single lightsaber there is in the universe? Nope, just one is fine. Can a Jedi own two lightsabers? Yeah, you're just looking for one, but if you have two, hey, that's fine too. Is that okay?
Or a double-sided one.
Or a double-sided one, yeah. Then you will need to represent that. You will need a predicate to say, this particular object is double-sided. Is that okay? Are there any questions? No questions? Okay, so in the English version, this is what it means, okay? We're basically saying if X is a Jedi and X owns at least one lightsaber, then X is a proper Jedi. Okay. In other words, there are proper Jedis and there are not so proper Jedis. Okay, there we go. Is that okay? But the key of this particular discussion is why inside the prologue sentence is a free variable. As a result, the quantifier that applies to that is a there exist. That is the key of this discussion. Because now we have another thing that we want to express, and it gets really kind of difficult in a way to express it. Okay? So in this case, I'm going to start with the English version first. So let's get rid of the formatting. And we'll just start with this part here and say if X is a Jedi and X does not agree with any Sith, then X is a proper Jedi. And we'll use a different predicate this time to express this quote-unquote proper Jedi. But the problem with this in this case is we only have existential way to express stuff in the body. So the difficult part is it becomes difficult to express that X cannot agree with any cis. Is that okay? So the first attempt to do this, okay, I'm gonna zoom back out a little bit. Okay, let me. Okay, I'm toying with both the zoom of the browser and also the zoom of the Google document itself. So there we go. Okay. So the first attempt to do this is to say, okay, let's see if this works. Okay. Is a proper Jedi 2, okay, because I don't want this one to be linked with the other one. So I will say that, okay, X is a proper Jedi only if, okay, first of all, X has to be a Jedi to begin with. Okay. And there exists a Sith, okay, so Y is a Sith, is a Sith. So Y is existential. There exists at least one Y such that Y is a Sith. And then on top of that, we want to say that, disagrees with. Disagrees with. X disagrees with Y. Okay? In the original text, I used the word hate, but but Jedis do not hate, right? Hate leads to anger, anger leads to blah blah blah, and that turns your Jedi into a Sith. So we kind of correct that. So we say disagrees with, and I'm pretty sure you guys get the idea that the Jedis can disagree with each other, even, right? That's what they do in a council, to disagree. So now we can say this, but this is not really saying what we want to say, is it? Because this particular statement or sentence in prologue is really just saying that if X is a Jedi and there exists at least one Sith that this particular Jedi disagrees with, that would make that Jedi a proper Jedi. What about the rest of the Siths? Oh, they can agree, not a problem. If you at least find one Sith that this particular Jedi disagrees with, that would make this Jedi a proper Jedi. But that's not what I want to express. I want to say that if a Jedi does not agree with any Sith or disagrees with all the Siths, then that Jedi is a proper Jedi. So I'm not quite expressing what I want to express, but we have a problem because the problem is I can't really express this part here, which is a universal quantifier, when we only have a free variable being able to be linked to a existential quantifier, or there exists. That's the problem, okay? Is that okay so far? Okay, so we need to somehow change this and go like, okay, but how do we fix this? So one way to fix this is to utilize a particular transformation in predicate calculus. Okay, so we'll go ahead and talk about that one. It's in my notes already, but if I just kind of draw it here or write it here, it will become more relevant. So that has to do with something like this. For all x, px. Okay, so this is something that is original for some predicate p. I don't really care which one. I'm just saying that okay, there's a predicate p, and for all x, p of x is true. Okay. And then on the other side, we say, okay, but what if we can only express there exists, but we can deal with negation? So the other side, okay, I'm going to use a right, left arrow to basically mean is equivalent to, okay? Oh, it doesn't quite like that either. Does it want it uppercase? Nope. It just doesn't like that. Okay, we have to do it the long way. There we go, double-sided, double arrow. There we go. Okay, so now we're saying for all x, p of x is equivalent to, okay? The other side will first involve a negation, okay? Because we can't express negation in prologue. You can say not, okay? So inside here, we'll basically say exists x, okay? And then in another level of parentheses, we just say negation of p of x. Okay, so let's check out these two sides and see if they are really saying the same thing. The left-hand side is easy, okay? It's basically saying for all x, p of x is true. Okay, that's it. But the right-hand side is a little bit more convoluted because we have a negation on the outside, and there exists, and then another negation. But what does that mean? It really is saying it is not the case that there exists one x so that the negation of p of x is true. Are they equivalent? Okay. So the question is, okay, every x is p. Okay, that's what the left-hand side is saying. The right-hand side is saying at least there exists, okay, some x is not p, and then the negation of that. Okay, it is not true that some x is not p. So now the question is, can we say this? That's the question. What do you think? Just looking at these as English sentences, or kind of oddly formed English sentences, can we draw the conclusion that the left-hand side, which is every x is p for some kind of predicate, is the same thing as saying it is not true that some x is not p? Okay, if that is agreeable, then we have a way to fix this problem. Because then we can say, we can now define a kind of helper predicate, okay? So the helper predicate is basically saying is cis tolerant, okay? Tolerant, okay. Is that typo spelling? I think that's right. Okay, so this is a prolog sentence. So what qualifies as, is cis tolerant? Well, I guess if you find evidence that, this x agrees with, does not disagree with one of the cis, then that person is cis tolerant. Is that making any sense? Okay. So if the only thing I can express is disagrees with, then we can do this. Okay, we can say, go find me some cis. Okay, is a cis. Go find me a cis y. Okay, this is existential, such that the following is true. Okay, so we have to say this agrees with x, y, and that's the end. That's the end of this prolog sentence. Remember, we have to read this backwards. It's saying if x. Oh, there's one more thing. No, this is it. Okay, so give me a particular person, robot, or whatever. Okay, x. If you can also give me a y, which is a cis, such that x disagrees with y. Oh, I have to say not, don't we? Okay. All right, that's better. So the x agrees with y, then x is known as cis tolerant. Would that be okay? Okay. Let's look at the math symbol, and then we'll look at the sentence in English. Okay. So the math symbol to represent this, okay, is for all x. Now, how do I know x is for all? Why do we know it's universal?
It's on the x.
Because in the head, okay, this is a variable in the head, and all variables in the head are universal, okay? All right. But we also know that there's a y as a variable, but y is existential because it is only in the body but not in the head. Is that okay? So what do we want to say about x and y? Okay, we want to say that is a cis y and wedge negation of disagrees with xy. Okay. So when we look at this whole thing, right arrow implies that is cis tolerant. Okay. Is that okay? Not disagree is the same thing as agrees. Okay. So I'm just using a negation in this case so that we can flip the meaning. Is that okay? Yep.
Does epsilon mean is a or there exists a?
Epsilon.
How about backwards?
The backwards E is a there exist.
There exists, okay.
So at least you can find me at least one Y to make this true. Is that okay? Or not? Okay, let's look at the English version of this. Okay, so let's look at the English version, which I put in double quotes. Okay, so the English version of this is if X agrees with Y and Y is a cis, then X is cis tolerant. Okay. Is that part okay? Does it sound about right to you? Okay. Okay, so now that we know what is cis tolerant, which means you have to agree with at least one cis, then we can go back and use this to help us define what is a proper Jedi. Because now we can go back and say, is a proper Jedi 2, because I want to make this a different one compared to the first one. Okay, first of all, we want X to be a Jedi first. Okay, is a Jedi X. Yep.
Don't mean because you already have Q defined.
Disagrees with.
Yeah, you have one. Yeah, it's a proper Jedi 1. It's a proper Jedi 2. This should be is a proper Jedi 3 because otherwise you'll be overriding the previous definition.
No, but this one is wrong. I don't like this one.
Oh, okay.
Yeah, so we want to fix the problem with this one with, yeah, with what I'm typing right here. Okay, so now we can make use of the definition of is cis tolerant. Then we can just say, not the case is cis tolerant X. Would that be okay? So let's check out what this means. Okay, so in mathematical symbols, what this means is we only have one variable. By the way, we only have X in this case. So for all X, for every X, the following has to be true. Okay, something implies something else. Okay, right arrows. There we go. So what is here is really the body of the prologue sentence. So we have is a Jedi X and not the case is cis tolerant X. There we go. That implies is a proper Jedi 2 X. Is that okay? What about R2D2? Okay, first of all, there are two questions. Okay, how does this rule apply to R2D2? And why is this rule still true when we're evaluating R2D2? Okay, so those are the two questions. The first question is R2D2 a proper Jedi according to the proper Jedi 2 definition? Nope, because R2D2 fails the first requirement of being a Jedi. Okay, fine. But why is this rule still universally true even when we are considering R2D2 as a robot as X? Because of the implication, okay? Because this is an implication, let me highlight the part that is an implication. Because this one is an implication, which means when X is bound to R2D2, then is a Jedi in parentheses R2D2 is false. Well, that will make the whole conjunction false, right? So this entire conjunction is false because R2D2 is not even a Jedi, so we won't even need to consider whether R2D2 is cis tolerant or not. So if this part is false and we're dealing with an implication, what does it make the entire implication? The entire implication is true. So we don't have a problem of this rule being false when we are considering elements in the universe that are not even Jedis. Is that okay? All right. Are there any questions of this entire discussion up to this point? No questions? Okay. Well, in that case, let me ask you a question. If I do not state anything about disagreements, okay, like I state who is a Jedi, who is a Sith, but there's no evidence of anyone disagreeing with anybody else, what would that make Jedis. Okay, so we'll do it step by step. So we'll go with this particular sentence first, okay? And the assumption is we cannot find anyone who disagrees with anybody else in this particular universe. So what is going to happen here? We can find cis, okay, not a problem. We can find the emperor, okay. So the emperor, or what's his name, Cedius, okay. So we can find Cedius, who's a Sith, but we cannot find anything with this part here. In other words, there does not exist a predicate so that we can say X disagrees with Y. So what do you think it would make that particular thing? Would it be made true or false because of the lack of anything disagreeing with anything else? It'll make it true because you cannot find it.
Yeah, yes, there's no, I skipped this up.
Mhm.
There's no proper Jedis.
Yep. And because we're gonna find it, so that makes it true, which basically makes everything in this universe Sith tolerant. So without any evidence of disagreement, the agreement is implied. Is that okay? All right. Are there any questions before we move on? Because this part has to do with how to read a sentence in predicate logic or in prologue and understand what it translates to when it comes to logical equations, and basically also the meaning behind that particular prologue sentence. So there are 3 parts to each sentence that we talk about in prologue. Yep.
If they were, you couldn't find anything that disagreed, wouldn't it mean they agreed, and wouldn't it make is Sith tolerant false?
If you cannot find anything, the negation, let me go pick up the negation here. Okay, so this part here. So the lack of finding anything to make this true, make the negation true. And as a result, that will make every single thing in this universe Sith tolerant. Okay? All right. Are there any other questions? No other questions? All right, so let's move on to substitution, okay, which is a very mechanical thing, but we need to understand it because we want this to be mechanical, very, very mechanical. So getting back to the notes here, okay, we are moving on through this stuff here, and now we are moving on to substitution. So we are talking about the actual quote-unquote engine of prologue, or a very important part of the prologue engine, which is substitution. So we are talking about something like this, okay? So these are basically substitutions, and this is a set of 2 substitutions. So let's take a look at the syntax of one substitution. This is a substitution. We are substituting the variable x with the variable y. Okay, so we use y to replace x. That's a substitution. And in the second one, we have another substitution, but this time we are using a particular element of the universe, Luke Skywalker, to replace the variable z. Okay? So the slash does not mean division, like in C or C++. The slash really is separating, okay, what is the original thing and what are you replacing it with? Is that part okay? The concept of substitution? Okay. So with the concept of substitution, then we can look at these different rules, okay? If we have a predicate is a Jedi X and X is a variable, and then we have is a Jedi Luke Skywalker, can these two, using a substitution, can they become the same? That's the question, okay? And the answer is yes, okay? If you replace uppercase X with Luke Skywalker, which is a substitution operation, then is a Jedi X is the same as is a Jedi Luke Skywalker. In other words, we say that these two predicates can unify. They can become the same. Is that part okay? Okay, let's switch back to the example here. So we will go for something that's easier, okay, like this part here. So we'll just focus on the fact that we know that Obi-Wan is a Jedi, and the fact that we also know that every Jedi can use a lightsaber. Okay, the ownership is optional, but every single Jedi can use a lightsaber. Okay, so we look at these two specifically, and then we say, but how do we conclude that Obi-Wan can use a lightsaber? Okay, that's the question. So mechanically, I mean, semantically, you guys all make that link already. You know that already. But in terms of the mechanical part of Prolog, how does it make it work? So what I'll do is I'm going to pull these two to the end of the documents, just so that we can focus on those two only, so we don't get distracted by the rest of this slide here. Okay, so let me scroll this up so that we can just focus on these two. All right, so we look at this particular part of the document, and then we say, okay, now that we understand what each one is really saying, but how do we know that Obi-Wan can use a lightsaber, but mechanically, not using the semantics, but using the syntactic transformation to make this happen? So now the first question is, if I want to know if Obi-Wan can use a lightsaber, then I am binding that X to Obi-Wan. Okay, it depends on how you ask the question. If the question is, okay, can somebody tell me whether Obi-Wan can use a lightsaber, then we are binding X with Obi-Wan already. Okay, so let me just state that. Okay, if the question is, can use lightsaber Obi-Wan, okay, then X is bound to Obi-Wan, because that's what we're asking. That's what the question is. Now, because X is already bound to Obi-Wan, then the other X is also bound to Obi-Wan already. Okay, so is a Jedi X also has X as a variable bound to Obi-Wan. Then we look for then we try to confirm that. Okay, so now we try to confirm that Obi-Wan is a Jedi. Okay, try to confirm is a Jedi Obi-Wan, and that we can confirm because it is here. So that concludes the chain of reasoning, and then Prolog will then conclude with the answer that Obi-Wan is, in fact, can use a lightsaber. Is that okay? So that's a pretty easy one. Are there any questions? Okay. But the key part here is the substitution. When we say that X is bound to Obi-Wan, that's a substitution, because we are substituting X with Obi-Wan. But that's not only happening to the head of that sentence. When you substitute a variable with a particular thing, that substitution is universal throughout the entire sentence. So when you ask the engine and say, can Obi-Wan use a lightsaber, by replacing X with Obi-Wan, that replacement or that substitution is also going to happen to this particular X here. So the question then boils down to, is Obi-Wan a Jedi? And then the system will go through all the predicates and go, okay, can any one of these rules confirm that Obi-Wan is a Jedi? And yes, we have one confirmation here. If true, then Obi-Wan is a Jedi. Means that Obi-Wan is in fact a Jedi. Is that okay? But we can ask the question in a slightly different way. Okay? You can also ask the question, if the question is, can use lightsaber why? Okay. Then you're asking the Prolog engine and say, tell me everybody who can use a lightsaber. Okay. So in that case, what the Prolog engine would do is it will try every single element as y, and then it will, based on that substitution, it will instantiate the variables to the right-hand side, and then keep asking that question until it finds a confirmation, either yes or no, whether that particular element of the universe is can use a lightsaber or not. So you can ask questions in different ways when you're dealing with Prolog. It's really just like asking a real question. Okay, you can say, okay, can Obi-Wan use a lightsaber? You can answer with yes or no, or you can ask a more general question and say, tell me everybody who can use a lightsaber. And Prolog can make use of everything that it knows, the rules, and also everything that is known to be true to begin with, and use those predicates to answer the question. Are we doing okay so far with this particular example? Okay, all right. So getting back to the notes, okay, we basically have this concept of a substitution, and unification involves a substitution and two well-formed formulae. A substitution is called a unification if the two well-formed formulae involved become the same after the unification. So what that means, okay, when we use a substitution, if this is the set of substitution or substitutions, and phi is the predicate or the well-formed formula that we are applying the substitution to, then this is not multiplication. It is basically saying that we are applying the substitution S to the well-formed formula phi, okay? And the example is the predicate is, or the well-formed formula is a Jedi with the X as an uppercase. If this is our phi, and the substitution itself is a set that simply states, replace all occurrences of uppercase X with Luke Skywalker. When we apply this substitution to this particular well-formed formula, then we get the result of is a Jedi, and in parentheses, Luke Skywalker. So are we okay in terms of what a substitution is and the symbol to represent how we apply a substitution to a particular well-formed formula, or predicate in this case? Is that okay? So you just state the predicate first, and then you state the set of all the substitutions that you want to apply. And when you look at this entire thing, it means that, okay, let's apply substitution lowercase s to the well-formed formula phi. And if you start off with this, and the substitution is like this, then we end up with a result like this. Are there any questions about these particular terms? What is a substitution? What is a well-formed formula? And the result of a substitution? No questions? Okay, so for some people, okay, if you're having a really hard time to wrap around the concept of a substitution, the easiest way to look at it is really to look at the editor. It's the same thing as find and replace. Because when you use a find and replace, you have to state what you're finding and what you're replacing with. This is the left-hand side of the slash. This is the right-hand side of the slash. So that's the easiest way to look at substitution. Okay. So getting back to here, a unification is basically a substitution of that is a single substitution applied to two different well-formed formulae, so that after the substitution, they become exactly the same. Okay, so this is the part that really defines what is a unification. So S is a substitution, but S is also called a unification for two different well-formed formulae. If you apply the substitution to phi and you apply the same substitution to psi, and if the result of the substitutions in this case are the same, then the substitution S is also known as a unification. A way to make two things that look different the same. Is that okay or not? Any questions about the definition? Any questions about what really this means? Because this really is the part that we are trying to get to. This is unification. Okay, let's see how this applies to normal programming. Okay. How many people have written programs long enough to realize that you sometimes use copy and paste? Okay, a lot, okay. How many people do copy, paste, and modify? Because what you're pasting into requires some modifications, some different variable names, or the constants are slightly different. Okay, I do that all the time, okay?
You should write a function.
Sorry?
You should never do that. If you're going to reuse code like more than once,
Mm-hmm.
then you should just put it in a function
Yeah.
and just use that instead.
Yes.
Because that's better practice.
Wait,
We're doing for operator outputs.
Absolutely, but what does that have anything to do with this? Okay, so let's check out what does that have anything to do with this. Okay, so let's just say that in multiple places. Okay, let's focus on just this. Okay, let's say at multiple places of your program you find yourself copying, pasting, and modifying code like this. Okay, so I'm going to give you the code. In many of my classes, I like to use this as an example because people actually do this a lot, and it is fairly easy to use as an example. Okay, so let's say you're saying, okay, if x is less than y, then z is x, else z. Oops. I like to use extra curly braces. Okay, so to make the proper syntax, we use semicolons at the end to turn expressions into expression statements. Okay, there we go. Okay, so when you look at this code, you kind of know what it's doing. Okay, it's trying to find the minimum of x and y, and then x becomes the minimum of those two. But as you work in your program, you copy and paste this in multiple places, and sometimes some of these may be just constants too. Okay, so in some cases you may say if score is less than 0, then minimum score is 0. Okay, because you don't want it to drop below 0. Oh, score. That wouldn't work too well with it. Fine. Flip these two. Okay. Okay, there we go. So you're trying to find the minimum of these two and then say the minimum score is either 0 or the score itself. Okay, because I'm assuming the score can go negative in this case. But the point is, does this code, okay, let me highlight this portion here, resemble in terms of structure of this code? Okay, they have the general structure. We are comparing. We are setting a third variable to the minimum of the two that are given to us. So even though this one is a 0, the other one is a variable, but they still go to the same places, right? Okay, so now the question is, what does this have anything to do with substitution, the stuff that we are talking about? Instead of applying substitution, we are trying to do exactly the reverse of that. So what we are trying to do is to find out, well, if I want to unify these two chunks of code, what can I do to make a function to unify these two chunks of code? Does that make any sense? Because I don't like copy, paste, and modify, so I want to define a find-min function to do all this. So what do? You find out all the differences between the code, right? So you say, oh, okay, so let's check what is the same, okay? The same part is there's a conditional statement, the same kind of comparison, okay, very good. The same kind of structure where we have the then portion updating z to the first part of the comparison. We have min score updating to the first part of the comparison. The else part is also consistent because we have z updating to y, which is the thing that is larger, or in the else branch it means it's less than or equal to x. And then in this case we have score being used to update min score. So we are doing exactly the opposite. So now we say, okay, let's go ahead and define a function. Let's define, because I'm a C programmer, I'm not a C++ programmer, so I just use int, and we say, actually we can make it a, I'm just trying to find out what is the best way to do this. Okay, I'll do this like this. Find min2, int x, int y. Okay. And we just say if x is less than y, return. Okay, technically speaking, I should use a local variable r. So we say r is x, else r is y, and return r. So now, with this particular definition of phi min 2, in the first case, then I can say x of z equals to phi min 2 xy. In the second case, I can say min score is phi min 2, 0, and score. Is that making any sense? Sort of? Okay. But what does it have anything to do with substitutions?
The parameter for substitution.
Exactly. So when you look at this, okay, when you look at the prototype of a function, particularly when you look at the parameters, they are to be substituted by something else, right? But when you look at the way you call a subroutine, when you look at the actual invocation of a subroutine, it involves substitution because you are substituting a parameter. In the case of x and y here, like we should have chosen the different names for the parameters. But in this case, we are substituting the parameters with the arguments. So every time you call a subroutine, it is a substitution. It's an application of substitution. What about the unification thing? The unification thing is exactly the opposite thing. You are basically looking at the two chunks of code that are very similar but slightly different. And you say, how can I unify these two pieces of code into a single subroutine? So what you're really asking is, what can I turn into parameters so that these two chunks of code would look exactly the same? Is that making any sense? So you look at the way we use x, and you go like, okay, all the places where we use x, let's try to turn these into a parameter I. And all the places where we use y, let's turn both of these into j. And in every place we use z, let's turn all of these z's into r. That's one substitution, okay? But you're abstracting the code. But you apply the same thing over here. You say, okay, let's turn all the zeros into i's, all the scores into j's, and then we turn all the min scores into r. So with those substitutions, would that make these two chunks of code look identical? The answer is yes. So now we have a unifying substitution for these two chunks of code. Is that kind of making sense or not? So let me just restate that, but this time in terms of substitution. So in this case, I'm going to define my substitution like this. Okay, so S is a set of certain elements. Each element is a single substitution. So in this case, I am substituting x with I. I'm substituting y with j. I'm substituting z with r. Okay, for the first chunk of code. For the second chunk of code, I can put it here too. It doesn't really matter. I can use the same set here. So for the second chunk of code, I'm substituting a 0 with I. I'm substituting the score with y, with j, sorry, and I'm substituting min score with r. Okay, this is a set of individual substitution elements. So now, if I call the first chunk of code, okay, so we'll go ahead and define this one as phi. Okay, phi equals to blah blah blah. This chunk of code, and then I look at this chunk of code and say, okay, let's call that a different name. Let's call that psi. Okay. There we go. Is that okay? So phi is this chunk of code. Psi is this chunk of code. This is my substitution. So now we have a unification because now we can say S is a unifying substitution because insert formula equation, because when you apply phi s, it really is the same thing as psi s. Is that making any sense? So you have been learning all of these concepts all along when you write programs, assuming you cannot tolerate copy, paste, and modify all the time. Once or twice, yes, maybe we will let it slip. But when you have like 20, copy, paste, and modify of the same chunk of code, you might want to think, maybe it's time to turn this into a subroutine. So are we doing okay so far with this example to illustrate what is substitution and what is unification? Okay. In predicate calculus, not only do we have unification, which we just kind of explained, we also have what we call the most general unification. So let's take a look at the definition of the most general unification, and we'll see, okay, does it make sense? What are we talking about? So by definition, G, lowercase g, is the most general unification for well-formed formulae, phi and psi, if and only if the following is true. Okay, so what is the following? The following is this chunk of nonsense. Okay, it's nonsense when we first take a look at this, so we want to kind of look at it as individual parts, and then we say, okay, but what does it really mean? Okay, first of all, we have an implication. Okay, we have an implication, and then we want to say, okay, what about this implication? So the implication is inside this whole thing, so we want to see, okay, what is outside here? This is outside of any quantification. So the first part that you need is, in order for G to be a most general unification, is to say that it is a unification to begin with. Okay, it kind of makes sense, right? In order for something to be the most general blah 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 unification, it first has to be a unification. Just like in order to be a proper Jedi, you have to be a Jedi first. Okay, so the first part, which is the highlighted portion here, simply states that G is a unification. Okay, but is it the most general? We don't know yet. Okay, the second part will tell us whether it is the most general or not. Is that okay? All right. So we first know that G is a unification. Then we look at this part here and go like, okay, so the real big part of the nonsense is this part here. So what are we talking about? Okay. So the first part says, okay, this is a universal quantification, which means for all S. Okay, consider all possible substitutions S. Okay. Okay, what about S? Okay, because S can be anything, right? Can be an empty set, can be some really oddball, substitution. So we say, okay, what is inside here is an implication, which basically means, yeah, go ahead.
Can't you click on that to make it pop out bigger?
You mean this part?
Yeah.
I can probably just zoom in. And maybe one more level. There we go.
Thank you.
Sure, no problem. Okay, so we look at this implication and say, okay, with every single implication, what you need to do is to look at the first part first. Because if this part is not true, we don't have to worry about it, right? So we only have to worry about the second part if this part, I take it back, if this part is false, we don't have to worry about it. If this part is true, then we have to look at the second part. So the first part is saying that S is a, come on, we just encountered that term starting with a U. A unification, right? Okay, so for all substitutions S, the first thing we need to say is to say that, oh, okay, but we don't want just any substitution. We want S to be a unification between phi and psi, okay? Okay, so given that S is a unification, what are we talking about? So now we focus on this part here. But you can see that I don't read the entire sentence from end to end. I kind of look at it in a nested way, right? So by the time we get to this part, we already know a few things. We know that G is a substitution and is a unification. And we want to know whether G is a most general unification. We also know that S itself is also a unification. So now we look at this and go like, okay, what about S prime? Okay, so this is basically saying, oh, there exists an S prime so that the following is true. Okay, so what about this following thing? Okay, this time we have a conjunction. It is not an implication, so we need both of these to be true for the entire thing to be true. So S prime is used in this case. Okay, so the first requirement of S prime is this. What is that saying? I use extra parentheses to kind of indicate the relationship between G and S prime. Okay, so we focus on one thing at a time. Okay, we focus on this part here. So we are first applying G as a unifying substitution on phi. Okay, so that gives us some kind of result, right? So we look at this result here and say, oh, we're not done yet. Let's also apply S prime to it. Okay, and as it turns out, this really is the same thing as applying substitution S to phi. So that's the first requirement. Okay, we want to get back to phi S. Now, what do we know about phi S versus psi S?
Same.
They are the same because S itself is a unifying substitution. And then we do exactly the same thing over here, which is basically saying, okay, we first apply the G substitution, but after we apply the G substitution, we'll apply that S prime substitution. But when we combine the two substitutions, G and S prime, we end up with the same thing as S. Is that okay? So now the question is, can we find an S prime to make this true? Okay, because if we can, for all S, then for all S there are actual unifications. Then we can say that G is the most general one. Is that making any sense or not? Let's look at it in a different way, okay? So we have G, which is suspected to be the most general unification, but we don't know whether it is or not. So we want to confirm that. Then we say, okay, let's consider all the other unifying substitutions. If you can re-express every single other unifying substitutions so that they all have the common core component of G, then G becomes the most general one. Is that making any sense? Sort of? Okay, we have, let's see, how many minutes? We have 3 minutes left. Okay, so if I go back to the example of the two chunks of code that I want to unify, the question is, once you unify, the question is it the most general way to unify it? That's the question. And I can give you the answer to that one too, and I can say it's not. Let me switch back to that slide. It's in the Google document. I'm so used to having my notes for the class in a different document. So I'm claiming that this really is not the easy. This is not the most general unification. There are other things I can unify as well. You go like, what? This seems to be the most universal way to unify that two chunks of code. So what else can I do to make this even more unifying? So I'm claiming that this is not the most general unification. So what thing can we abstract out even further? We can take it out and go like, okay, let's make that also a parameter. Now in C code, I'm not a C++ programmer, so I'm not going to tell you guys how to write it in C++, but in C, we can do something like this. Okay, this may not be.
It works in C++.
Yeah, it will work in C++, but most people have not seen this before. Okay, so I'm passing compare as a pointer to a function. In other words, I'm not saying use less than. Okay, just give me some comparison. Then I can unify this even further by saying, okay, I don't know exactly how you want to compare, but however you pass whatever function of which the address you pass to me as a comparison function, let's use that here. So I can say, use whatever compare points to, and apply that to xy. That becomes a more general unifier than what we had earlier, by parameterizing the actual mechanism of comparing. Yep?
So I'm trying to kind of hash out your use of the prime notation. And I'm kind of getting what's going on here.
S prime is really just another substitution, which is kind of doing the quote-unquote leftover of G, so you can get back to S. Okay, because G is the most general one, the most general, right? So when you apply S prime, it makes it more specific. Huh?
We're trying to get as generic as possible.
Yes, that's what we want. So what this part is really saying is every other substitution is more specific than G. That's all it's saying. In other words, if S is more specific, that means after you apply G, there's some leftover things that you can still apply to make it more specific. Yeah, the same thing that we just did. So the S prime is quote unquote the leftover part, so that you can turn the G substitution into the S substitution, which is a more specific and less general unification substitution. What about G itself? Because when we say here for all S such that S is a unifying substitution, but doesn't that include G as well? But what would happen to S prime when G is really S already? What do you think we have to do to S prime? Remember, S prime is a set, right? So how do you say I don't want to do any substitution? What set do you use?
A null set?
Yeah, exactly. You just specify an empty set. So we don't have a problem with G being a part of this S here. We just specify S prime to be empty, and that makes it happy. Okay? All right, so we are running out of time today, so I'm gonna close today's class, and nobody reminded me to upload the recording. Oh, you're just about to? Okay. So I'm gonna do it right now, and I'll see you guys on Wednesday. Huh? Yes, the assignment is due on Wednesday. The
Right?
say again?
The fundamental, I think it's called the fundamental counting theorem. Okay. I looked it up and
I feel like I didn't know if I
found something called the fundamental counting theorem,
Okay.
where you multiply them together, and it gives you like,
Yeah, when you multiply, it means, this is one independent way to choose that thing, and then that's the another way to choose the next item. That's when you use the multiplication.
okay.
So let me upload this real quick. You can ask the next class to come in because this might take me a little bit of time.
Okay.
Yeah, thank you.
Is it in the millions? I think it was, okay. Hopefully. The other one is not as big? The one that's due on Wednesday?
Right, it's fine.
Yeah, we're losing.